Okay, welcome everyone to episode 3 in season 1 of our exciting mini series entitled Additional Problems, which you can download from Sakai. This episode is entitled Deep Impact, and the reason for it will become obvious in a second. So looking at problem 3, you see that you've got two disks colliding along a coordinate system xy, which is shown in this diagram. I've already drawn it. The disk A comes with 10 meters per second, B with 8 meters per second from the opposite direction. Now, this may not be the smartest coordinate system for us to use. The force between disk A and disk B is actually exerted along a direction between A and B in this fashion here. So the force is exerted between the two centers of mass. So if we want to choose a coordinate system where the force is only acting along one direction, then we need to choose the coordinate system where our x-axis or y-axis lies along the line of impact like this. I'm going to call this system here x bar, and then this is our y direction like this, and this y direction here I'm going to call y bar. Okay, what we're also given is a triangle like that, where we've got the hypotenuse equal to 5, then we've got a 3 and a 4 like this, and that is supposed to help us with our angles when we relate from the one coordinate system to the other. So our first thing that we want to do is, since we want to use this coordinate system here, the x bar and y bar coordinate system, as opposed to the old coordinate system, just x and y. What we want to do is we want to express this velocity and this velocity here in the new x bar and y bar coordinate system. We've been given some help in the sense that we've been given this triangle here in the x and y coordinate system, and for instance this angle here, if we look at the geometry, is going to be exactly equal to this angle here, and then if we look at this, it's also equal to this angle over here, or for instance the other angle on that side here. Now our strategy is going to be that first we're going to express our velocities in the x prime y prime system, so velocities in x bar and y bar system. Then the second thing that we're going to do in order to be able to calculate the x and y velocities is to use momentum conservation. Along which direction? Well, along the x bar direction, and then also and y bar, but we know that the y bar is going to be easy because there's no force acting along the y bar, so the initial and the final velocity along the y direction are going to be the same in the x bar y bar system. And then since we're going to have two unknowns here, the final velocities along the along the x direction for body A and B, those are two unknowns, we need another equation, and that equation is given by the equation of restitution. So we're going to use restitution in order to obtain then our final velocities. I'm going to call them V2A and V2B. So those are the two final velocities denoted by a 2. So for instance, this here is velocity V1A and this is V12. Okay, so the first thing that we want is we want the velocities in the x prime and y prime system. So what we're going to do is we're going to rotate it like this, and then what we want is we want this component here and this component here. So you can see this component here is the y component or the y bar component, and this component here is the x bar component in the new coordinate system. And then this component here is the x bar component of velocity of body B, and this component here is the similarly the y bar component of body B. Okay, so if we write this, okay, I'm going to write this just now, but I'm going to denote this one here as V1 because it's an initial velocity. It's of body A, so it's A, and it's along the y bar direction, so bar. So this is V1A y bar. And this velocity here is V1A x bar. Okay, so that's for this velocity here. So that is the x component. This one here is V1B and y bar. And this one is V1BX bar. Okay, so that is how I'm going to denote the components of these velocities. Okay, so that's in the new system. So let's work them out. Okay, so we start with body A. Let me write down here. So first we work out the velocity. So body A has got along the x direction, that would be V1A x bar, which is equal to the velocity of 10 meters per second times, and then if you look at this angle here, looking at this angle, so we've got, so that angle is the same as this angle here. You're happy with that? Okay, this one here and this one here is the same. And similarly, we're going to have this one here the same as this one. And if I'm going to call that angle theta, this one, then this is theta, and this is theta, this is theta, this is theta, and subsequently this is also theta. Okay, so I'm going to have 10 times, and that is cosine, so for the x direction, cosine of theta, and for the y direction, I'm going to have V1A y bar, which is just 10 times, and then sine of theta, and that I've worked out to be minus 6, because remember, maybe I should put that in, the x component goes along the negative direction, so this should have had a negative sign, and that's got a positive sign. So that's minus 6 meters per second, and that's equal to 8 meters per second. So that's for body A. For body B, along the x direction, and these should have been bars. So that's along the x bar direction, that's the velocity, and along the y bar direction, that's the velocity. Along the x bar direction, then the velocity is, the initial one is V1B x bar, and that is just equal to 8 times, and then also cos theta, and then along the y direction. So this velocity here, let's have a look. This velocity here, V1Bx, so that's this one. Oh, and we see there's a negative sign, so we must put that in because, sorry, I lied to you. That should be a positive because it's this direction. V1Bx bar, V1Bx bar is this one here, and the V1By bar is going to be a negative, carry a negative sign because it goes in the negative y bar direction. So it's minus and then sine theta, and if you work them out, then they come to 4.8 meters per second for the one, and the other one is, what did I work it out as? It was 6.4 meters per second. So that's 6.4 meters per second. So those are all the components now of the velocities of these dark velocities here. So of everything that's in the black coordinate system with the black velocities, that's what we've worked out here. So those are all the black velocities. Okay, so this one here, for instance, is minus 6 meters per second, and so on and so on. Okay. Okay, great. So now what we're going to use is we're going to use momentum conservation. in order to obtain, in order to make some progress towards working out all of these velocities. Okay, let me start like this. So, writing down the momentum conservation equation along the x prime axis. So, we now work out word number 2, momentum conservation along x prime. Okay, so what is the initial velocity along x prime? Well, it is, I can write it down in the form first like this. So it's MAV1, that's the initial velocity, A along x prime, plus, and then MB, V, the initial velocity of body B along x bar, is equal to then MA velocity 2. So that's the final one, A x bar plus, and then MB velocity 2 B x bar, like that. And if we're putting in the numbers, what I get is 15 times minus 6 plus, and then 10 times 4.8 is then equal to 15 V2A x bar plus 10 V2B x bar. Okay, great. This gives us an equation that looks like this. Minus 42 is equal to 15 V2A x bar plus 10 V2B x bar, like that. So we've got an equation with two unknowns. What do? We need another equation, and that other equation is given by restitution, by the equation of restitution. So we write down the equation of restitution like this. It is E is equal to V, the final velocity along B along the x prime direction, minus the final velocity of A along the x prime direction, or I'm calling x bar x prime, it's the same thing, in the initial velocity A x prime or bar minus V1B x bar. I'm throwing in the values, and what I get is 0.8, which is what our restitution coefficient is given as, is equal to V2B x bar minus V2 and then A x bar divided by 1.2. And then I can call this equation here equation 1, and I'm going to call this equation here equation 2, and then using 1 and 2 in order to eliminate say for instance anyone, either the final velocity of along the x direction of either A or B, I get for instance V2A along the x bar direction is equal to 2.1 meters per second, and I urge you to do these calculations. So just solve for this one, and then substitute it in here, and then solve for V2B x bar, or and then for body B, the final x direction is equal to what I get is 7.2 meters per second, which is fine. Okay, so these are the final velocities along the x directions of body A and body B. Okay, so this is the hard work, this is where the force happened. Now, the question is, what happens along the y direction? Well, the final velocities along the y directions are just equal to the initial velocities along the y direction. So there's no problem with that, and we can very easily determine this just by reading off the final and initial velocities along y. It should be like this. Okay, so along the y direction nothing changes, and that is the end of this problem. Thanks.